I moved from Chicago to California like 20 years ago, and I remember living in the Midwest that you'd go to like a wedding or some kind of event, and like the weird cousin would always come in from California, and you could tell because they weren't wearing a tie. And you're like, oh, there's that weird guy from California. And I have gone completely native. And so nothing brings me more pleasure than coming to Washington and presenting in a t-shirt. All right. So I want to talk to you today about kind of like the state of the world, really high-level stuff, history of technology, and we'll sort of get a little bit into the weeds about cybersecurity at the end. There won't be a quiz on this week, but this material might be on the final. So, all right. So I'm Ari Gesher. I work at a place called Kairos Aerospace, and we'll go into the details of what that is for a minute, or in a minute. But previous to that, I spent 10 years at Palantir Technologies. I was engineer number 5. I sort of joined up when it was just a crazy idea. Originally, Palantir is one of the most misunderstood companies in the world, mostly because it doesn't really talk about itself, especially since I left. I was like the one guy that they sent out to talk about what we did. Originally Palantir was focused on solving something very specific, which was the intelligence failures around 9/11. Basically looking at how data was not flowing between agencies and building all the software infrastructure and analysis tools that you'd need to solve that sort of problem. Over the years, it's acquired a lot more different missions, moved into a commercial space, and it's still one of the most misunderstood companies in the world. The thing that's really interesting about Palantir is that they've decided to stake out a new place in the marketplace, which is instead of doing services or products, which are sort of two polar opposites. One is I'm just going to sell you something and you're going to figure out how to use it, or you're going to pay me for my time and I'll build whatever you want, but there's no guarantee that I'm going to build the right thing or that it's going to be efficient or anything like that. Palantir says, let's price outcomes. Let's figure out what change you want to make and leave the details to us. We'll come in, we'll partner with you and figure out how to do it. It's a very interesting journey. It's not one that is over yet, but if it works out, it may be a whole new way of doing software. There's a lot of beliefs about Palantir, that they're collecting data about everyone, that they're some privatized CIA. None of that is true. Palantir is basically just a software company. But Palantir is actually very interested in how you be a data owner and have data about people, data subjects, and do that in a way that's responsible. So there is a privacy and civil liberties team at Palantir that sort of looks at this and gets involved in the technologies around that. And Palantir has built a lot of stuff into their stacks for that. I was sort of privileged to be able to work with them. And around the time that this guy started talking to the world, we as a team sort of pitched a book to O'Reilly on this topic, and we co-authored The Architecture of Privacy. And this book is a little bit different than any of the other stuff on privacy out there. I know cybersecurity and privacy often overlap, so this might be of interest to people. Most of the stuff on privacy is all about policy. Like, what are the rules that we're going to have about handling our data? This is actually a practical guide to building data systems that have privacy-protected features. So it's a very high-level architecture manual about how you think about actually building systems that implement those policies. As a subtext, it's sort of written as a love letter to the that's the wrong slide. Sorry, to the NSA, as in, like, given the Snowden revelations, what would be sort of the thought experiment of how you could do these sort of things, but do them responsibly. I decided not to become a privacy expert professionally, and go into work on climate change, which is what Kairos is about. Before that, though, I worked at SourceForge.net back when I was sort of the maintainer of SourceForge.net back when it was relevant for the young folks in the audience. That was GitHub before it was GitHub. It was the world's largest open source archive for a long time. So that's me. The place I want to start in actually talking to you today is actually with the Industrial Revolution. So why the Industrial Revolution? Well, the only way to sort of understand the present of technology is understand the history of technology. And in recorded history, the Industrial Revolution is the first time that humanity went exponential. So understanding that sort of tells us a lot about our current condition. So very briefly, the Industrial Revolution is that people realize that if they burn carbon and they do it in the right way, they can use it to actually do work. And they say, oh, wow, that could be really useful. And as soon as they figure out that how to use that in the right way, it does become very useful, and the whole human world goes exponential. So here's 12 different graphs measuring like various things in the world, like everything from like the number of McDonald's to urban population, real GDP. They all go exponential, and it's all based on this sort of injection of potential energy into human work, right? That we sort of dig, the Earth has been storing it for tens, hundreds of millions of years. We dig it up, we use it, and it went great. Like, it transformed the world. It let us build things like the most powerful machine ever built, the Saturn V rocket, took us to the moon. It wasn't without its consequences, however, right? So here's 12 other graphs that are also exponential about the environmental consequences of the Industrial Revolution. And so it's everything from the amount of CO2 in the atmosphere to like the destruction of coastal zones, loss of rainforest, etc. I mean, this is not news, hopefully, to anyone. But this is where Kairos Aerospace comes in. So most people think about global warming is being caused purely by the amount of CO2 in the atmosphere. CO2 is a big part of it, and CO2 is actually the long-term problem. So the problem with carbon dioxide is that on human timescales, it has an infinite lifetime in the atmosphere. Once you put it there, you got to figure out how to take it out, or it's going to stay there forever and absorb infrared energy and leave it in the atmosphere. But methane is also actually an enormous problem with global warming. The difference with methane, like methane absorbs about 84 times as much energy as CO2 does, but it has a limited atmospheric lifetime, so it breaks down. So instead of having to figure out how to pull it out of the atmosphere, all you have to do is stop putting it there, and it'll go away. And there was some research that started about 5 or 6 years ago. They first published in 2016, that they found that most of the methane, the sort of the methane imbalance coming from oil and gas, was actually just from leaking infrastructure, and not from what you'd think, which is like the aggregate of like tiny little leaks coming out of like valves and gaskets, but actually enormous leaks out on remote infrastructure that nobody checks and nobody sees for a long time. And so the original founders of Kairos, I sort of knew them. I was actually gave them their first angel check while I was still at Palantir, are a couple of astrophysicists who worked at Lockheed Martin. This is Steve Diker, our CEO. They literally went to the garage and sat down and designed a spectrometer that they thought from space could actually see methane plumes in the air. This is on the right is Kepler, on the left is Luna, the dogs that are usually around our office. So Steve's here at the table. Right next to him, that little black box is the Mark I spectrometer. Here's the view from the table across the street. There's a sun mirror there, and Brian, who you can barely make out, is like holding a balloon in front of the sunlight to actually test it. So that test was successful. Spoiler alert. And it led to the Mark II spectrometer, which is our current production design that we actually use. The big lens leads into some infrared optics. This over here, this is an infrared camera that we actually use to image the spectrum, a portion of the infrared spectrum in the air. The little one is an optical camera. We plug in power and Ethernet over here, and we hook it up to some single board computers and strap it to a Cessna, right? So here you can actually see, this is a unit inside the Cessna through a vertical photography port, which is a fancy name for a hole in the floor. And the other one in the sort of split screen you can see is out strapped to the strut of the Cessna inside that fiberglass pod. The operator's sitting here with two laptops, both connected to two different Wi-Fi networks to actually to control it. And here are the sort of the control surfaces, which is a web interface to do it. The data looks something like this. When it comes in, this is sort of the blown-up view of the CCD sensor. Those vertical dark lines. So each row is actually just a point on the ground, and it's been spread spectrally. So each row is sort of the bucketed histogram of wavelengths in a particular part of the infrared spectrum. Those vertical lines that you see on the right side and the one right in the middle, those are actually methane molecular absorption lines. So we are seeing global warming. That is the missing energy that methane keeps in the atmosphere. If we pull out one of those lines and look at it as a graph, it looks like this. This right here, this is the edge of what gallium arsenide can see. So this is where we stop being able to see photons with those energies. And then those dips, those are the molecular absorption lines. So based on this, and compared to some sort of background, we can actually measure methane in the air. We record a GPS track, which lets us lay it down on the ground. This is just infrared brightness. It's not a measure of methane, but it lets us see that we're matching the underlying ground features. And that allows us to produce images that look like this, right? So this is a busted flare stack somewhere in Texas. There's a pipe there that's supposed to be burning methane as it comes out, but it's not. This looks like about 3 different passes over the same stack that are laid on top of each other. This was sort of, I think this was not, well, this might have been a production flight. But what's happened in the 4 or 5 years since we've been working on this, is we've got it working. So we just finished a 1,200 square mile survey in Texas, and here's all the stuff that we found leaking. And each one, like our system only sees really big leaks, so each one of these leaks is the floor for what it can see is about 50,000 standard cubic feet of natural gas per day, which is like enough to power 7 homes or something for a year in terms of the total energy that's being released per day from each one of these leaks. And the other thing that's happened is the science is pretty settled that this is the case. So now there has been literally in capital S science additional research that shows that there's about a 60% surplus from what the reported leak levels are of methane, and that's all coming from these super emitters. So I'm a little busy these days. So that's my day job. So I threw Palantir under the bus, I threw privacy under the bus, and now I'm just working on climate change because I like working on big problems. That's the end of my introduction. I'm happy to answer any questions. I can talk about that for literally weeks. Yes. Thank you. I appreciate it. I actually feel really privileged and fortunate to be able to work on it. One of the weird side effects that I didn't expect is that as Rome appears to burn around us, I get up every morning and not have an existential crisis, because I can be like, oh my God, everything is messed up, what should I do? And the answer is, oh right, I should just go to work and work on the thing I'm already working on, because that's a really big problem. So I feel sort of, it's almost like a luxury these days. Okay, but that's not what I'm actually here to talk to you about. I want to start this narrative here with Stuart Brand. So anybody here know who Stuart Brand is? All right, good. Good that you know. But so Stuart Brand famously published something called the Whole Earth Catalog. And Stuart Brand was this guy who was almost like a tribal ambassador during the early days of the counterculture. He hung out with like Ken Casey and the Merry Pranksters and could just sort of move around and observe everything that was happening. And there was this sort of philosophical movement in the late 50s, early 60s as a reaction to the notion of cybernetics. So in the 50s and 60s, post-war, like this is like the height of industrial revolution, societal makeover. People are thinking about things like organizations made of people working like machines, right? And this is sort of the beginnings of early cybernetic theory. And there was actually a sort of a reaction to it, which led to parts of the counterculture and this whole, like, there was a back to the land movement where people set up a bunch of communes. Whole Earth Catalog was designed to be a catalog of various tools that you could like mail order that was a repurposing of this sort of industrial might to a smaller scale, so that like people on a humane scale could actually like use these things. So it was all about access to tools. Now, the back to the land movement ended up failing because it turns out that anytime you set up a bunch of communes, it basically just ends up being they turn into sex cults, basically. Like it's all about like little mini dictators and authoritarianism, and all just kind of falls apart pretty quick. So that didn't really work out, but it did have a lasting effect on the culture. And Brand, as you get to the 80s, sort of shifts his focus to software, right? So one way to think about the PC revolution is it's actually this embodiment of the notion of repurposing of industrial tools into the hands of a single person, right? In the 50s, there was like famously some estimates that I think it was IBM, like had a forecast that the worldwide demand for computers was going to be like 5, like very, very small. Like that mainframe era that turned into the microcomputer era is this sort of democratization of that technology. And so in the 80s, there, like with the Homebrew Computer Club and the rise of microcomputers, software became this sort of thing to traffic in. So there was the Whole Earth Software Catalog. And that then sort of transitions, and Brand doesn't really have a hand in it, but that whole ethos transitions into open source, and it gives us, GNU and Apache and Linux and Android and Hadoop. And today we sort of take for granted that any serious piece of software that's going to be used for infrastructure is open source. Like that's just like understood, which is a little weird. I mean, it comes out of the fact of like software's economics that you can actually give away copies for free, that the marginal cost is 0. But that access to it, like anybody can get Linux. Like Linux is the substrate of the modern. I work with a lot of cloud stuff now, and it's really weird to me that like the world starts with like pound, bang, bin, bash. Like that is like the beginning of all of modern technology. You're like, wow, that's That's from a while ago. So we have, we reach this height with the Industrial Revolution, but the interesting thing about the Industrial Revolution writ large is that it actually happens before the world really goes exponential. So the Industrial Revolution starts in about 1740 with the first steam engine, which someone's like, well, I don't know, what can we use this for? Well, if we burn the coal to run the steam engine, we can use the steam engine to pump the water out of the mine that we're mining the coal from. All right, that sounds good. So that's like the very beginnings of the Industrial Revolution. And for 100 years, people are trying to figure out how to use this. They're developing the technology, making it more accessible, applying it to problems. And it's not until you get to like the mid-1800s with like the advent of like transcontinental railroad and steamships that suddenly the world goes exponential. So it's not the invention of the technology, it's actually the human timescale of people understanding how to use it and apply it that you have to wait for, and then the effects are profound. I want to read you this quote. A spider web of metal, sealed in a thin glass container, a wire heated to a brilliant glow. In short, the thermionic tube of radio sets is made by the 100 million. Talked about in packages, plugged into sockets, and it works. Its gossamer parts, the precise location and alignment involved in its construction would have occupied a master craftsman of the guild for months. It is now built for 30 cents. The world has arrived in an age of cheap, complex devices of great reliability, and something is bound to come of it. This is from 1945, right? Vannevar Bush, one of the original, like the guy who oversaw the Manhattan Project, oversaw NACA, the sort of the progenitor of NASA. It was very clear to him what was going on at the advent of digital technology, which is right around the end of the war. And we've come a long way. Some would call it the second machine age. I did not come up with that. There's a great book on that by these two guys. If you're interested, the first one got us to the moon. The second one, we've been riding this wave of Moore's law. So some people like to actually backdate it before the advent of digital technology to show that the curve is exponential all the way up. But where are we roughly today? Right, here's the Intel Xeon Phi Night's Landing, 8 billion transistors, 3 billion floating operations per second. And maybe a couple $1,000. Maybe actually this one is a couple generations back, maybe it's a couple $100 now. This is a Banana Pro. It's sort of a Raspberry Pi clone. This is actually the single board computer in our first revisions of the pod that we actually used to control the cameras. $45. Actually, they stopped making it, but you can, it was $45. This is more powerful than the first workstation I used to do software development, right? And a good way to think about it is today it's got like a dual core ARM. It's about as powerful as an iPad, right? And these things are not just cheap; they're also ubiquitous in being repurposed. So, like here is the 3DR Solo, the first generation smart drone. You can think of this as basically a flying smartphone. Like the only reason that these are so cheap is because we have smartphones, and the thing that you need to power this is basically smartphone guts. A lot of people like to talk about man portable drones. I like toddler portable drones, so that's my daughter carrying my 3DR Solo. And how do we get to this? It's interesting because it's sort of like a mashup of two different revolutions that is embodied in actually the big, the Saturn V is a great example, but there are only like 6 of them made. Like, what are the real sort of hulking giants of the Industrial Revolution? The answer is container ships, because they are everywhere. But container ships are like this interesting mashup of, like, we're going to get this big ship and we're going to put some oil in, it's going to move a bunch of stuff, but we need to do packet switching of physical goods, and that's sort of more of a digital technology. And so the thing that has enabled the global supply chains today is cargo ships, right? Or intermodal transport, as it were. And we see this in adoption curves, how fast things move into ubiquity, right? So here are various technologies, and you can sort of see their adoption curves. The details are not super important, other than understanding that the further we get to the right, the more vertical those lines look. That as soon as the adoption of smartphones happens so incredibly quickly compared to, like, say, the telephone. If we shift our focus and look at this from a proliferation standpoint, things get kind of interesting. And by proliferation, I mean arms proliferation. One way to view the Iraq and Afghanistan wars is that they were a cell phone war. You can't really have IEDs without cell phones. I mean, you can, but it's actually very difficult. Like the technologies you need to do really good remote triggering that can't be jammed and that sort of thing, that often requires a proper nation-state military. But the world runs on cell phones now. You can't just shut them down. And it's very hard to pinpoint who's got what cell phone and what's going on. So cell phones make the perfect trigger for IEDs. And it's a very, very difficult thing to counter, and it's great for an asymmetric actor to use as a way to deal with a big army that's coming in. I remember I was actually at Black Hat for this presentation, which was 7 years ago. A couple of researchers put together for $6,000 an RC aircraft and a couple of like cell phone, like GSM hotspots, something with 45 minutes of loiter time that you could sit over a target. It had a connection to the cloud to do Wi-Fi cracking, like it could send things up to the cloud to do GPU-based Wi-Fi cracking to break into people's networks. And you could just sort of loiter over someone for $6,000 with off-the-shelf components and basically have your own little ISR bird that you could just follow somebody with, right? So, and it keeps going, right? So this is from a year ago, and something like this was actually in the news just a couple weeks ago, which is that those UAVs are great little like targeted assassination birds. Like the 3DR Solo has a payload bay. You can put 300 grams of whatever you want inside the payload bay and trigger it. Like there's a little USB line, you put in some electronics. It's like almost tailor-made for that. Like these are not things that people think about when they're like, let's build the iPod of drones, right? Which is what the Solo was supposed to be. They weren't thinking about it as a target assassination weapon. But you can't, like, how many DJIs are there in the world today? How do you actually stop those things from crossing borders? Like, you don't. The next supply chain that is spinning up, and I see this in California, is autonomous vehicles. So there are now companies that just build LiDARs for autonomous vehicles. There are now companies that actually, this one really blew my mind. I met a guy, his entire business is generating virtual miles for autonomous car AIs to drive. So, like, you model your sensors properly as sort of like drivers that you plug in, and then you plug in your AIs, and then you can drive in parallel on the cloud, so you can get millions and millions of miles, right? So there's this huge supply chain effect coming up around autonomous vehicles, but all of those things, if you repurpose them, are really great for building weapons. And if every car in the world, or even a small fraction of cars in the world, are autonomous, there's no way to actually stop those technologies from moving around. And we haven't even gotten to the next step, right, which is just starting, right? Like a DNA easy bake oven. So there are some obvious takeaways from this, right? One of them is just that military technology has historically been linked to an industrial R&D like base and R&D capacity. That's no longer true, right? These like the desire for technology globally on a consumer level means that these supply chains spin up. There's no way to control that technology. It can go anywhere in the world. That means that asymmetric actors can actually get access to these technologies really, really easy. And in fact, the time from invention to ubiquity is dropping exponentially, which means the time that we have to react to such things is very, very small, and to understand what those unintended consequences might be. The non-obvious takeaways are that repurposing systems are getting easier because of a long-term trend towards open systems, right? So like if I build a LiDAR unit, I also have like really great data sheets that are going to come with it because I need to sell it to all the people who are going to use it. So instead of that being sort of like proprietary information inside a company, that's now sort of open information that can be used to integrate it into something else. And the accessibility of technology is increasing. And this sort of goes back to what I was saying about the Industrial Revolution, how long it took. Like accessibility is not just about how easy it is for people to use the technology, but also how accessible the problems are to the technology, how easy it is to actually apply a piece of technology to a problem. And what we're seeing is that there are lower educational barriers to using this stuff, and there are market dynamics that sort of favor platform plays, and anytime you have a platform to play on top of, it's a really great fulcrum to leverage whatever it is that you want to do. As an example, the 3DR Solo, I'll use that, which is still, again, it's bad. Like there are much newer drones now. The base station, like the controller, actually runs Linux on an embedded system. It has an API endpoint on the controller, and if you just and it comes with an SDK. So if you hook up your laptop to this controller and you can write some Python, you can programmatically control one of these drones to do whatever it is that you want to do. And so the barriers to entry there are very, very low. in terms of controlling a population's access to, if you wanted to do such a thing, to that information and to the technology you need to integrate with it. And so the intersection of cheap, ubiquitous, and easy to repurpose is just going to continue to grow. Now, this is out in the real world. What does this have to do with cybersecurity, right? And the answer is actually in the cybersecurity domain, this is not really new. I'd call this the old normal, right? Attackers have the same tool chains as defenders because it's all open source for the most part. There is an asymmetry that actually favors the attacker, right? Because defenders have this enormous surface area and attackers get to hide wherever they want. Security practice is about preventing the subversion of tools and the exploitation of flaws. So it's about stopping things from being used in ways that they weren't intended to. And these days, infrastructure at scale can be stolen or rented. I have witnessed personally the leaking of an AWS access key that was exploited within 8 minutes to launch as many instances as possible mining Bitcoin on someone else's dime and burn through $25,000 in a few hours of EC2 time. AWS reacted to it, like notified the person, and they were able to shut it down, and they rescinded the bill. But like 8 minutes, someone like published it on GitHub, and like machines were launching. So what might work against this? The thing to do is double down on automation, but that's actually the beginning of the story. It's not the end of the story. Don't build fully automated tools, because AI will fail, and I couldn't have asked for a better presenter to come before me to point that out. And the reason for this is that cybersecurity is filled with adaptive adversaries, right? And so, at its core today, still machine learning is all about using statistics about the past to make predictions about the future, and if the future is different than the past, good luck. And which is not to say that techniques have not gotten pretty advanced. They have. There's a place near me called the OpenAI Institute, and one of the ways that they're training up their AIs is having them play video games against human players, and they've become some of the best players in this game called Dota, which stands for something, I'm not sure what. They beat some of the best teams out there, although just like 2 weeks ago, they were beaten by a professional team. And people analyzing the results of this found that even though the AI is very, very good tactically and can almost win any engagement that they're in, it only has a strategic window of about 14 minutes. And if you can sort of plan your engagements on a much larger scale, you can actually beat the AI, because it's really just looking at its environment and can't sort of play the larger game unless it's sort of learned to do that, right? So don't build fully automated tools because pure AI will fail. Instead, use human-computer symbiosis as an architecture to make defenders bionic, right? So the idea is that you always need to have brains in the loop. But what you need is automation to sort of sift through the noise as much as possible, to recognize anomalies and bring it to brains. And this was sort of the central design ethos that we used in building a lot of the tools at Palantir. And it's interesting because a lot of stuff like the Vannevar Bush quote, there's a paper that it was anachronistically named Man-Computer Symbiosis, today we call it Human-Computer Symbiosis, by J.R. Licklider, who was at MIT and oversaw a bunch of sort of interesting projects there. The paper came out in 1960, and it basically just says, yeah, one day machines might think, but they don't now. And so what you should do now is automate everything that can be automated and present to people all the information they need. And like he points out, like that as a researcher, much of his time was spent just like laboriously plotting out graphs. And when you're done with the graph, the answer is right in front of you. But all the work goes into actually making the graph. Now, we don't make graphs anymore because we have Excel, and we sort of we let the computers do that today. But that finding actually holds on everything that we do. And so you end up with a mix of needing like really good data processing and a really good user interface to present that information, to give people the ability to very quickly sort of express what they're doing. And that's a topic that I could wax on about for hours. But then the other thing that actually is important is like being able to apply AI quickly to new domains. So new domains of information that come up. It's like a lot of the focus in sort of the tech press on AI is about new techniques that might be interesting, but increasing the accessibility and applicability of AI to problems is sort of paramount, and that's the only way to sort of get ahead of the attackers in this domain. And I want to leave you with a new problem that we have been hearing a lot about lately. This is, I think, the new term of art coming out around this, which I think will end up pretty solidly in the cybersecurity umbrella over time. And this is sort of the new normal, and that is tools with exponential reach that are used as intended, but they're used for nefarious purposes, right? So Facebook ads, it's a very good example of this, right? So you actually have these enormous surveillance platforms that have been built, but they're consumer surveillance platforms for delivering ads to people. And so there's the sort of the headline stuff about Russians placing ads to influence elections, but there's also some other stuff where researchers are actually looking like how much money do you need to spend to track an individual target. So if you can micro-target your ads to a person, you can actually figure out where they are, and you do it with somebody else's infrastructure that's used to just deliver ads, right? And so why would I get 20 people to tail someone if I can just watch their check-ins on Facebook or whatever it is? And this is a thing that we haven't really thought about. In fact, one of the things that has led to this, which we may in the sort of the historical view see as a huge mistake, is this legal term of art called safe harbor. So, these various platforms, the Googles, Amazon just is infrastructure, but Facebook and Twitter in particular are what we call Web 2.0, where Web 2.0 was Web 1.0 is I have some stuff I'm going to put on the web and anyone can go and see it. Web 2.0 is I'm going to build a place for other people to put stuff and then to give to other people. So Twitter and Facebook sort of, we all make our posts on there, and social media is Web 2.0. And the regulation around them uses a legal term called safe harbor, which is to say that the owner of the platform is not responsible for the content on the platform. If there's any ever problem with it, they need to take it down, but they don't need to proactively guard against that. And what that allowed them to do was exponentially grow really, really fast because they didn't have to solve any of these problems. They could sort of do that ex post facto instead of ahead of time. And so it leaves us in this sort of weird place. And this is from Singularity Hub for our cartoonist who works there, but about people's inability to understand the consequences of exponential growth, which is that humans are actually very, very linear, and we think very, very linearly. But these exponential growth factors and all these things, they grow way faster than we can possibly imagine. And so our predictions are often really, really off. And you see this in all over the place, like with Moore's Law and all of its friends, in sort of applied research into miniaturization, but even things which I guess is related, like solar panels and the rise of renewables, all those curves beat everybody's expectations because nobody knows how to really estimate an exponential really well. So the advice that I give you is look for those exponentials and figure out how to get ahead of them, as it were. And that's all I have prepared. I'm happy to dive into any of this. I would love to hear what questions you have. Yes? Oh, yeah. It's possible. I mean, one of the great things actually about, serverless is sort of the new pinnacle of the cloud. And one of the things that's actually great about the cloud is that we don't have a bunch of wasted effort. So I don't really want to have a security team. I'd rather use Amazon's security team. They do a really good job of hiring people and figure out how to build in sort of that platform level security to all their infrastructure. Serverless may actually be an innovation that is a great reaction to the sort of the n squared, the sort of exponential explosion that you have in trying to actually defend your own infrastructure. If we only have one set of infrastructure and we put all of our best effort and best minds into protecting it, it's going to be more, not perfect, but more impregnable than if everybody is sort of self-performing that. And so using things like serverless, for people who aren't familiar with serverless, the idea is it's not actually serverless, it's just somebody else's server. But the idea is I can write a bunch of code, instead of having to get a computer to run it on, I can just upload it to the cloud somewhere and it'll run inside some kind of managed environment. So Docker sort of is part of this, but things have gone even more serverless with what are called just serverless functions. In AWS speak, it's a Lambda. But the idea is I can just write a little bit of JavaScript, a little bit of Python, put it somewhere, and I can chain all these things together. And then I don't ever as a software developer, I don't ever have to mess with infrastructure and getting that wrong. So I can just focus on the thing that I'm trying to build. So I could be totally wrong here, but is that serverless is actually going to increase security in the world because it reduces the possibility of people who don't know what they're doing, or people who even do know what they're doing, making mistakes. There's just fewer opportunities to make mistakes. So I think it'll be a net positive for security in that regard. Oh, yeah. Yes. No. So I guess there's two different ways to do this, and you're absolutely correct. So on the one hand, serverless makes it easier for me to secure my infrastructure in terms of making it more difficult for an attacker to get into it, because I now have absolutely the best practices and the best people and the best infrastructure working on securing my stuff. So my opportunities for making mistakes are lessened. The flip side of that is it reduces the effort of an attacker who wants to leverage large infrastructure against me. So if I want to be like and this is a theme that I end up dropping from the talk from time, is that software developers today who understand the cloud using infrastructure as code are maybe the most highly leveraged human beings in history. Which is to say, with the smallest amount of effort possible, you can marshal incredible resources very, very quickly. And so that is a thing to worry about. It doesn't mean like if you have a billion nodes but I don't have any holes in my infrastructure, having a billion nodes just lets you knock me off. Like we just get into an arms race. So having that capability makes it easier for us to get to the point of an arms race where we're just seeing who has the bigger stack. And it does aid asymmetric actors in terms of being able to steal or rent that infrastructure to have the scale that you would get from a much larger organization who could perform the building of that infrastructure. It means that we have entered an era where like you can't just rely on your own scale to win, which is maybe the way that I would think about that. I would leave this thought as an aside, but related to this is that people who know how to use the cloud today are the most highly leveraged humans. Like the way that we do things at Kairos, for example, we do use infrastructure as code, and we do things completely ephemerally. So we don't just write programs and then run them on computers. We actually write programs that create computers for us, then put the software on the computers, then put the data on the computers, then run the computers, then take the process data off the computers, and then tear it all down. And that happens in the course of, like, with no human intervention in the course of hours. And so, like, when we like run a day's worth of data, which is about 30 gigabytes of input, it needs about 5,000 CPU hours of processing to produce those images. And that all happens. We spend a couple, $500-600 to process a day's worth of data, and we do it with like something like 4,000 CPUs running simultaneously, which if we had to buy that infrastructure would be insanity. So from a non-cybersecurity standpoint, it's sort of a golden age of frictionless computing. But when you use that for nefarious means, yeah, it means that everything is easier. And you don't have to be able to have the resources to marshal that infrastructure.